Bob asked for a presentation, and we got to talking a little bit. My other interest is radio-controlled airplanes, which I build and crash. And anyway, he said, "Well, how about something on, how the radios work?" And I thought, well, that'd be kind of interesting because they're all spread spectrum now. Used to be that, it was 72 megahertz, or if you were a ham, you'd get a 50 megahertz radio. But if somebody else got on the channel with you, you went home early that day because the plane crashed. But now it's all spread spectrum, and that's kind of cool because now you can have 20 guys flying all at the same time and nobody interferes with each other. So that's kind of neat, but what's even neater than that is that spread spectrum is found everywhere. And it's the basis for our cell phones, for our Wi-Fi, for GPS. And so although I've kind of got my hands-on type stuff is all focused on the radio control thing, we're going to look at spread spectrum in general. Now these two people here were young and beautiful during the Second World War, and they figure prominently in spread spectrum. One was Hedy Lamarr, the famous actress and beauty, and the other was George Antle, and they developed essentially spread spectrum that has morphed into what it is today with all our modern technology, and they received a patent for it back in 1941. And the inspiration for spread spectrum was to obscure messages, classified messages from the Nazis. And this was essentially by using various frequencies to, transmit your information on. But although it had its beginnings in World War II, spread spectrum didn't really catch on until the Cuban Missile Crisis in the early 60s. And that's the first time it was implemented on naval ships and used for military communications, obviously to obscure communications from the Soviet Union at that time. And it developed from there, and as we already mentioned, makes possible Wi-Fi, cell phone, GPS, cordless phones. Yes, it's used in cordless phones. I remember when Sony first came out with their first spread spectrum phones, they didn't work worth a damn. but they finally got that figured out.
Is it frequency hopping, or is that the other kind?
Hold the thought.
Okay.
Excellent question. Excellent question. So what is spread spectrum? Well, it's basically you're going to take a signal and you're going to spread it out so that it fills the entire available bandwidth. So if your bandwidth is, say, 10 megahertz, and you start out with a 1 megahertz type signal, you're going to spread that out to fill the full 10 megahertz. Now there's some trade-offs to doing that. We'll show you what that is. But the advantages are essentially you've got noise reduction, you've got security, and the most important is resistance to jamming. In other words, interfering signals. So here we're looking at a typical narrow band data signal. Now, this would be your carrier and your modulating data, right? With spread spectrum, we're going to take this signal and spread it out. And notice that the frequency increases. And also notice that the overall amplitude decreases. You still have the same amount of power, but the power is spread out. Yeah. And this is where it gets a little confusing, but we've got some diagrams to explain that concept. So here's kind of an important thing to keep in mind, and we'll explain this a bit more. That the total integrated signal density, or signal-to-noise ratio at the receiver input, determines if there will be interference or not. Well, that's true of any signal, right? Whether it be regular single sideband or FM or whatever. In other words, there's a threshold at which you can't understand or decode the signal anymore, right? But what's interesting about spread spectrum is this, that the signal-to-noise ratio is basically a ratio of the RF bandwidth, in other words, how much space you've got to spread the signal out, to the information bandwidth. In other words, the actual data that you're wanting to modulate and transmit.
So all things being equal, spread spectrum SN signal-to-noise ratio is inherently better than narrowband.
Yes, and we'll see why momentarily. And now to Craig's question, how do they do it? Well, there's essentially two methods. One is called direct sequence spread spectrum, and the other is called frequency hopping spread spectrum. And they take two completely different approaches to achieving essentially the same aim. Let's take a look at this first one. With direct sequence spread spectrum in the transmit mode, the carrier is going to stay fixed. So whatever your carrier frequency is, that stays fixed. And then the information, which is narrowband, is modulated and spread out by adding, they say it's a random sequence, but it's not a random sequence because the receiver's got to know what the sequence is. But it's often referred to as a pseudo-random sequence. But for all practical purposes, it's random in that an outside observer wouldn't know what the next bit of data was.
So that requires that the seed value is transmitted initially so that it can be decoded?
Or that the receiver is already programmed.
It's hard-coded. So
It's hard-coded,
yeah.
yes.
Yep.
So in this diagram here, they're showing, okay, here's the amplitude, and then we're going to add this data, and the result is that the bandwidth increases, but the overall amplitude decreases. So you think, oh, hey, this is down in the noise, how are we ever going to find it? Well, we'll get to that in just a second. But this is the concept with the direct sequencing. We're going to actually add bits, and there's a slide coming up where we're going to show you. Essentially, it's a two-step process to achieve this. Now on the receive side, we have to despread it. So in this diagram, we're showing, all right, here's your spread spectrum signal, and here's some RFI, some jamming signal right here. Now, when we receive the signal, we have to generate the original narrow band signal, and that's called despreading. And when you despread it, your amplitude goes up, but guess what happens to the jammer? It goes down. And in most cases by at least 90%. And so your despread signal is way stronger than your jamming signal.
That's assuming that the jammer was up jamming on a narrow band frequency. What if he was jamming on a spread as big as wide as you are?
Then you're screwed. Yeah, good point, Paul. Excellent point, because is this foolproof? And the answer is no. It's not foolproof. But in real world, unless somebody's intentionally trying to do this, then you're going to be okay. And so let's say you have 10 or 20 spread spectrum signals like this in the same bandwidth, right? But because they're all going to decode with a different algorithm, then they will not interfere with each other.
Well, that's answering Paul's question to some extent, isn't it? Couldn't you have two different stations on the same band, but just one has a different sequence, so they're both there, you can still decode it, right?
Well, that's true. But if you have a big jamming signal that is, jamming.
Oh, yeah, okay. Yeah,
Broadband,
broad
spread spectrum.
Right.
okay.
Thank you. Yes, broadband non-spread spectrum.
Okay.
Then
If they're following the rules, you can overlap, but if they're not following the rules, it's off.
correct.
Okay.
Correct.
Yes, the other thing that happens is, if he was gonna have that high a power across the entire bandwidth, it would take a lot of power to
Correct.
change that amplitude across that band.
Correct. And that would have to be something very intentional.
Oh, yeah.
Yeah.
I mean, it would have to be strong enough to wipe out everybody.
I have a set of cordless telephones at home, home wired phones, but 3 cordless handsets that I think works on spread spectrum. But what if my neighbor has, a bolt built by Panasonic, a bolt, whatever, identical.
Different formula, though.
Yeah, but they've got a different the algorithm to encode and decode is different.
That seed number,
Yeah,
Right.
the seed number
The
would
seed
be.
number.
so they would put a different
Yes.
seed number
Correct.
in every phone.
Right.
It's like drugstore openers.
Right.
It's not like usually pre-coded, other than like if they're prepared at that, but usually it's generated either by an initial synchronization. There's like a part that's, transmitted. It just happens to be that, you turn this on at this time, and then it's synced up. Or they're, internally they pick from, there's a pseudo-random algorithm, and then, they just have a, sync process that sets them to an internal value that's the same.
And your neighbors wouldn't necessarily.
Yeah, theoretically they could line up, but you'd quickly resolve that
But
by
drugstore
repairs.
openers could be the same, but they probably aren't.
Yeah.
It becomes a mathematics problem if your probability is very low.
If you were going back to doing it with a computer, generating random numbers, you give that algorithm a number to start,
Right.
okay? And from that number, it knows how to generate the next one in the sequence and on and on and on. So that if you're doing modeling or something, you can always come back and reproduce that exact same sequence of random numbers,
Yeah.
okay, by starting with a seed.
Right.
Now, the other choice is to pick a random number to be that seed, and then you don't know.
and you can never reproduce
But
it.
that goes back to just plain, every computer will do that. Okay, or actually, every computer language has some facility to do that. So when he talks about pseudo random numbers, that means it's a random number generator with a known starting key. Right. So it'll always produce the same sequence of random numbers.
And amazingly, it works. Now, how about frequency hopping? Now, frequency hopping uses a different scheme. Essentially, what they do is they just keep moving the carrier around within the available bandwidth. So we're not reducing the overall amplitude, but we're just moving the frequency around. Now, what does this mean? It means that the receiver has to know where to go listen next, right? And it also means that once it hops to the next frequency, it has to lock onto the signal, right? And takes time, yes. And so their latency is higher than in the direct sequencing. Now that said, frequency hopping seems to be extremely popular. And it also works very well. The new chipsets permit the receivers to lock up super fast. And so the latency issue is not what it used to be.
Is the timing random or fixed between from one hop to the next?
It's a pseudo-random, it's generated. So when you pair the receiver and the transmitter, they know.
There are schemes out there that apply to peer-to-peer wireless communications in the digital realm between microcontrollers, where the time slot is fixed, the window's fixed at least. So you have an opportunity in the code to catch on the receive side the signal and lock.
Right.
Right. You have a set window, but without a GPS or something like that to use as a reference point, you can't tighten that window up much. You have to allow some slot.
So I'm going to show you here in a little bit example of frequency hopping and how the transmitter and the receiver initially established that.
How fast would they hop from one frequency to another?
Depends on the design.
Milliseconds, no problem.
Yeah, milliseconds, yeah.
It's much faster now.
Yeah, it's microseconds today.
Yes.
Yeah.
It's the whole, you spread out over the bandwidth, so it'll be faster generally than like the data rate.
Yeah, faster than
Sometimes, I mean,
Well,
there's two different ways.
Before
Yeah,
it slows it down, right?
yeah. You either send a burst of data in one with you. DSS is always it's faster than the data rate, but it could be a burst and then another burst, which is OFDM, but otherwise it's the same piece of information transmitted on multiples sometimes as well.
And a lot of it has to do with the actual chipsets being used. There's a lot of variation possible. So let's talk about modulation a little bit. Direct sequencing uses the encoding signal to modulate the carrier, whereas not so with frequency hopping. But both systems require a unique code. The actual information modulation can be done with either AM or FM techniques. So that's not really important, and essentially whatever the designer determines. Now, demodulation. For DSS, we have to remove the spread spectrum modulation, and this will become a little more clear in the next couple of slides. And with frequency hopping, we have to synchronize to the frequency carrier as it changes before we can demodulate the signal. And then the remaining information, the original data that we want to move from point A to point B is demodulated or decoded. So let's give an example. CDMA, we've all heard about CDMA. Code Division Multiple Access. It's a form of DSS. And here we're saying, all right, we want to send a binary 1. We're going to take the spreading code right here and add it with the binary 1, and we're going to get this result. And this result is what's going to be used to modulate the carrier and spread our bandwidth. Think about it. If you just wanted to send a binary 1, that would be a relatively narrow bandwidth, right? But here we want to send 5 bits. That's going to be a wider bandwidth. Now this is kind of a very elementary example, but it shows the concept of what's going on. So here we take our data stream and we combine it with our spreading signal or our chip sequence, and then use it to modulate our carrier, and this is our CDMA signal output. And the spread signal. On the receive side, we take our received signal, we inject our carrier, and then we add the spreading sequence, and that results in the original data stream, which is what we want. So that's your de-spreading. It's actually a 2-step process.
Steve, I gotta take off, but thank you very much.
You bet. You might be thinking, CDMA, my phone's GSM, right? And they're both spread spectrum, but I thought I'd throw this in because, you know, when you think, okay, CDMA, GSM, what's the difference? Well, essentially, phones on CDMA networks don't need SIM cards. That said, all phones have SIM cards because if you want LTE, then you need a SIM card. And you need, if you got a smartphone, you need a SIM card. But anyway, technically, CDMA networks are SIM card free, which means that they are tied to a carrier. Whereas GSM, which stands for Global System for Mobile Communications, they do require a SIM card. That's what they use in Europe, and it's a more universal system. So in the United States, CDMA networks are Sprint and Verizon, and GSM networks are AT&T and T-Mobile. So you can take your T-Mobile phone to Europe and easily, you know, get it to work there. But if you've got a Sprint phone, not so easy. So, spread spectrum advantages. Reduce crosstalk, it's a big one. Better data integrity. They're more immune to the static type noise that's generated in industrial and home environments. I mean, think of all the things that generate noise in your house. I've got some LED light bulbs that just generate all kinds of noise. Less susceptible to multipath fading, which is if you're going to do something with RF remote control, that's a big thing if your device you're trying to control is moving around. More secure because of the pseudo codes that are used, and it makes it harder to intercept and decode, although that said, that's a problem that smart guys have figured out. So anyway, and this one here, multiple systems can operate in the same space. That's a big thing. So phones, right? In the case of my other hobby, remote control airplanes, that's a big deal. And so there's just tons of advantages. Now, if you want to get into designing spread spectrum, that's not for the faint of heart. There are kind of off-the-shelf solutions for it, but for those that are actually programming the code and everything, that's
You could do a very simple version of it, for example, all right? With a DDS, for example, it jumps real quickly and put your own pattern in there. You just say, I wanted to start here and take this pattern, jump there, and synchronize with the receiver that does the same sequence. You can go at your own speed, at your own simple version. I was always thinking of doing that with my SI, the DDSs, because they program very quickly. You could jump them and send data over them. And I'm not sure if that's the part that's permitted on the amateur bands or not. I know you have to, some parts of spread spectrum are available on real high frequencies, but I'm not sure what the limitations are. If you can make your own sequence and go ahead and program it or not.
Yeah, I was kind of leads into my question, which is from, on HF,
Yeah.
not VHF and UHF, but on HF, what's been holding it back?
Well, I don't know,
It's not a technical.
You'd have to have it be a
It's
public
bandwidth,
algorithm.
but you're sharing it at the same
but I
time.
don't think it's legal though. I don't think that.
No, it isn't.
FCC
You can't have encoded.
I understand that.
What? Yeah,
Why?
but why? Well, yeah, I'm sure it's because of noise.
Why is it illegal?
Well, it brings the noise floor, right? For everyone.
You can do that with JT9 or JT65, and
You
raise
can limit the bandwidth then.
and you limit the bandwidth. This would say that you take a
Yeah.
slice of spectrum,
Right.
gentleman's agreement,
Yeah.
right,
And live with it.
and live with it,
Yep.
right? And
Yep. Yeah.
as
And
an
I'd love to play with
experimental
that.
thing,
I would love to play with that.
what would be the big deal?
Isn't the legality that, like you can't use the high-speed burst CW stuff from World War II because, FCC can't hear can't figure out what
That
we're
was the
saying.
part of it. You would have to publish your sequence or something.
Yeah, your
So that
sequence,
you're
and you
not
have to be able
hiding.
to sync with the
It's always
sync over
seemed to
there.
me that we needed a band, and 10 meters would be a good one because it's got so much bandwidth. To do all
That's right.
holds barred, right? Basically, no holds barred, and you can do whatever you want. Experimental.
And not even publish your sequence or whatever.
Right.
So, yeah.
I mean, who the heck's using all the 10
Well,
meters?
but they're worried about that find this and drug runners or something start using
Well, I
that.
suppose that's what comes up every
And
time.
But it would be fun to experiment with. I mean, I thought about that for years. And it is fast enough that you could jump to a new frequency quickly enough that you could do a simplified version of it, just on a home hobbyist type thing. It would be fun to play with.
Have 2 frequencies.
No,
Go back
between
and
5 or
forth.
6 or 10 frequencies. You just add a contact to it and go to the new one and wrap around and
Even 2 would make most
even
people.
2 would be fun.
Then you could use 60 cycles on both ends.
Whatever.
But most people wouldn't be able to figure out what you're saying.
Right,
you know?
right. And that-
Well,
if you're
today,
sitting on-
the point, I guess, partially too, is there are so many ham operators that have GPS decoders and such, and it's gotten the price point on them for the cheaper units is dirt cheap now. I mean, there's a lot of technology that's within reach to do this. But somebody would have to take up a petition at the ARL and try to drive it through, right? It's, you know, to what benefit is it? Well, you could probably make an MCOM play on it or something since it is high signal to noise ratio, but, you know.
Once again,
They can do it today with regular Wi-Fi. They can, and
yeah.
we even have a lot of the, I can't remember the frequency, but the regular, normal Wi-Fi modems that we have in our
Broadband. Yeah, it's 2.4 gigahertz. We're allowed up at 2.4.
Right,
And
on some of those.
Certain channels are.
So you can take a regular Netgear wireless
Linksys,
modem and
Linksys
put it,
have them, yeah.
and put power on it, and antennas on it as much as you want, and be
Absolutely.
legal
Mhm.
on the handband.
As long as you turn off all the encryption and don't transmit
Yep.
any encoded data.
See, that's the big one. Jeremy hit the nail on the head, it's the encryption.
So basically, you can't use the internet these days.
That's the thing, I think if we looked into it, or someone looked
Does
into
the
it, they would-
Wi-Fi itself do the encrypting?
If you have it set up for like a WPA or
Oh,
WPA2
okay.
stuff, you have to do it open network.
I mean, that's
Oh, yeah.
No, that's right, but that's, I think, part of the fear, it's like you said, you know, it was rum runners at one time, and drug runners, now it's terrorists, I mean, there's always gonna be some boogeyman there that's, they can use it.
Yeah,
as
they
an
don't care what the
excuse.
laws are, so, you know, they're gonna do it anyway.
Yeah.
Anyway.
No, but if we build it for them,
Well, yeah.
then they're just gonna adopt the technology and use it.
It would be fun. I mean, that's how you learn about something like this, by playing with it. You experiment with it. That's how you really know how it works and
Yeah.
develop a system to do it.
Well, I would say at low power and certain frequencies, you're not breaking any laws, right? At low power levels.
No one would come after you, is that like that? You might
Yeah.
be breaking lots of it.
Oh, yeah, maybe you would, whatever, but yeah.
Your signal doesn't make it outside house.
So let me polish off the presentation with a little discussion about servos.
Good.
Obviously, I use them. They come in all shapes and sizes. This is kind of a standard one. A lot of people wonder, well, how do they work, right? There's 3 wires, power, ground, and control to a standard servo. And these are what power all the robots and so forth. So anyway, it's very simple. Actually, for an analog servo, and there's 2 kinds of digital servos, which I'll describe in a minute. But for an analog servo, we need to provide a 1 millisecond pulse followed by your control pulse, which is a pulse width modulated signal, which can vary between 1 millisecond and 2 milliseconds. So here we're showing a 1 millisecond, or the minimum signal, and the servo is positioned to the extreme left. A 2 millisecond signal positions it to the extreme right, and a 1.5 millisecond signal centers. This is followed by a dead time that can be up to 40 milliseconds. Now, during this 40 milliseconds, that's when, for radio controlled stuff, you send the other channels. So you've got aileron, rudder, elevator, throttle, whatever. You can have up to 20 different channels. Although I've never seen a 20-channel remote control. Now, Mitsubishi makes a common chip that's used, and this is it. You can buy these dirt cheap if you want to build your own. Essentially, you have an input coming in on pin 5, and you have your position signal coming in on pin 1. And the position signal is courtesy of a potentiometer that is tied to the shaft of the servo. So as the servo moves, the potentiometer moves, and the voltage divider set up by the potentiometer changes. Very, very basic. And here's the sample circuit. You can build this circuit. It will work. Here's your potentiometer right down here. This voltage at pin 1 is changing. It's compared here to the PWM signal coming in at pin 5. It's a one-shot multivibrator that compares the incoming signal to the internally generated signal, and that develops your error output, which drives these transistors with the motor across it. That's it. Very low parts count, dirt cheap. I mean, you can buy servos for like $3, and they work, right? Now this is an analog servo. Now digital servos are becoming more popular, and digital servos come in two flavors. One flavor is essentially works like an analog signal, except it's got a little microcontroller in there that will more accurately hold the position. You're still going to feed it the same control signal. And then some of the new systems that are available will take the received signal and is digitized in the PWM. It does not come out as PWM control. It comes out as a digital word, and that word is sent to the servo, which decodes it and very accurately positions it at X number of degrees. So, anyway, I brought with me a,
Question?
yes,
What feedback do you use in digital word?
well, yeah, it has a potential, it can do a couple of things. It can use a potentiometer, or it can use like Hall sensors. The Hall sensors will give a more accurate control than the potentiometer will.
They all use digital encoder technology.
Sometimes. Digital rotary encoder.
Yeah,
Shafting
The
encoder.
digital word though is on that input pin. There is
Yeah.
no feedback normally that path, even with an analog. It's,
I mean sensors.
yeah. Okay.
right, so the transmitter says set the servo to 80 degrees. And the data goes out, it's received, and by the receiver then sends data to the servo that says set to 80 degrees.
And that step is analog?
I'm sorry?
That last step is analog? Or not? Digital?
No, the last stuff is digital.
So you've got a digital word that represents the number of degrees.
Correct.
How does it know it's at that setting? That's the sensor.
Well, inside the servo, there's a feedback mechanism which will represent how many degrees the servo is at any particular time. And that feedback mechanism can be a potentiometer tied to the shaft, or it can be like Hall devices.
It goes with both the analog.
Well, yes, but okay. So in the case of a potentiometer, then the output voltage would go to a DA converter. In the case of a Hall device, you also are going to amplify that, balance it, and send that to a DA converter, or A to D converter, excuse me. So yes, you're correct there. Yeah.
Another option, and I don't know if they have in commercial, would be to use a digital shaft encoder or a pulse counter we used to have industrial systems, we used a gear with 60 teeth on it, and we counted the pulses. One revolution was 60 pulses. And used that in the digital speed control and basically position control system.
And
And those things could use a digital encoder in there if they wanted to take them in.
yeah, absolutely, yeah. The only ones that I know about, and I don't own any because they're too expensive for my, you know, my pocketbook.
It'd be silly to have all the digital accuracy.
You need
resolution,
360
and then go
points in order to do
step
1
at the
degree
end.
of accuracy.
You've got subject to temperature and
Well, the Hall devices are very sensitive, or excuse me, accurate. But yeah, there are obviously other ways to do it.
The other thing that happens in these servos is they don't react immediately. You might have a load pulling that rudder one way or the other, and you might say, I want to neutralize it. It may take a while. It may take many of these cycles for that to actually come back to neutral. Okay?
The big drive for digital is to solve that problem. Because the old pure analogs were basically, they got the pulse and compared it and basically started the movement that way. And it took until a series of pulses to kind of like stabilize. Whereas the digital, it's like you could say, I know that internally it could, go back and forth as much as needed to get to that, even before the next cycle around.
I know what I've seen in the servos is the positive.
Yeah.
So anyway, what I wanted to show you was that this is a fairly new 2.4 gigahertz spread spectrum frequency hopping controller, transmitter. It's 10 channels with telemetry. All right? So that means that this receiver, and by the way, I'll pass this around, the actual antenna is the little silver part at the end, all right? The other part of the wiring, that's just coax. But this is an 8-channel receiver, and it does have digital capabilities, and I've got one sensor on here, and this is an altitude sensor, and this will sense the altitude within, I don't know, 20 feet, thereabouts, and it sends the altitude information back to this. So if I have it in, for example, a glider, I want to catch a thermal and climb, right? But other than visual, and it's kind of hard to tell when it gets up there, I don't know. But there's a jack on the back that I can plug a headphone into, and it will actually tell me rising, descending, or I can have it tell me the exact altitude, or I can set it up so that it vibrates one way. I'm holding it in my hand and it vibrates a little bit one way when it's rising and vibrates another when it's descending. So that's kind of cool. And yeah, and these things now have become like very inexpensive. This setup right here was $320, which is,
Who makes that one?
this is a Fataba. Now, I will tell you, for those of you that are kind of into hacking, there is a Chinese firm called FR Sky. They make fine stuff. It's dirt cheap, and it's open source. And you can do with it what you want. And finally, even though this is not ham radio or radio, I thought, well, maybe some of you guys would be interested in seeing, what powers these models. So I brought in a couple of electric and a couple of glow type engines. This engine here, a little electric, will power maybe up to 1 pound worth of airplane. This one here will power up to maybe 3 pounds, all right? And this is like $12, and this is like, I don't know, I think I paid like $20 for this one.
So is that, depending on how big the propeller you have there, is that what it's?
Well, yeah, and you have to match the propeller with the engine,
Yeah.
with the speed controller, with the battery. Otherwise, you get smoked. Now, for the glow, and by the way, glow fuel essentially is like diesel, all right? And I'm sure you guys are pretty well familiar with that. Here's a small glow engine that will power a plane up to about 1 pound. And they're fun. This is a little more robust engine. This engine will power a plane maybe about, you know, up to 5 pounds, and it's kind of the de facto popular size glow engine. And then this one right here is a 4-cycle glow engine, and this one will power a plane up to maybe 20 pounds.
Wow.
And you can
Is
see
that a
the
muffler on
props
there?
are pretty big, so you got to keep your fingers out of them. So,
Where's the radial engine?
that's a
They have 'em.
yeah, they have them, but
Single
you,
cylinder, huh?
you know, it's like ham radio. You can spend as much as you want.
You ever
And
see
they
that?
even have
Money too.
turbine engines. So if you YouTube stuff,
U-2
they,
B-52, about 6 or 8 guys in England built one that the tail was up to about here, had 8 turbine engines, and they had a failure.
So how crowded are the fields when you go to fly nowadays? Can you get in pretty easily?
oh yeah, yeah. Now I
Pick it up and landing and all that, there's not much people, or not people that are always in your way and...
no,
Really?
no, I
Surprisingly little activity in
Really?
the fields.
I fly with a club that flies right off of Highway 65 in East Bethel. And they've got a paved runway and a grass runway, and I don't know, they've probably got 120 members, and you can always fly. I mean, the field is always a good, nice day. There's always folks there, but yeah, you can always get in. And now with spread spectrum, it's great. I still have a
You still have
70.
the runway open though when you're ready to come in. I mean, you don't want somebody lining up with your...
Well, they have pretty strict rules.
Okay.
Yeah, there's strict safety rules because you can get hurt.
Yeah, yeah.
But at the club I fly with, they permit 5 people to be flying at maximum, unless you're flying combat. And then we've had as many as 15 guys flying.
Wow.
But that's chaos, you know.
Still want to put some SD's Rocky pods on a helicopter.
But anyway, spread spectrum, that's where it's at. And thanks, guys.
Thank you, Steve.